All right, how's it going? Hanging in there? Yeah. No football this weekend, I guess. Any questions before we get started today? No, all's good. All right. So we've got a short tier one coming in right away on Monday again, and then from that point forward, we're going to be on a Monday, Friday schedule for tier one, tier two. So it'll be pretty regularized past this first one. Okay, so to continue from Wednesday, we were looking at how to do state change calculations with the adiabatic compression or expansion process. So just to refresh your memory, we're thinking about this conceptual methane contained in a cylinder with the piston on top of it, and this time we're compressing the methane by very rapidly plunging the cylinder down until we get to the target volume. And we're doing it so quickly that there's no heat escape from the cylinder, or another way of thinking about it is the cylinder is so perfectly insulated that even if I'm doing the compression slowly, there's no heat escape. So all that mechanical energy is getting transformed into internal energy. And so by the time I get down to my target volume, so 4 times less than where I started, my final temperature is going to be quite a bit higher than my initial temperature. And so to get to state 4, I'm going to end up having to cool down when I'm done. Okay, so we got to the adiabatic expansion equation pretty readily just by a few straightforward manipulations of the differential first law balance, right? So we make the standard substitutions for the internal energy, for the work, for adiabatic. The dq term is going to be 0. And one of the first places we get is this expression right here, which once you turn it into the ideal gas system, you get an easy substitution for pressure. And now you've got a 2 variable system that can be directly integrated. And this boxed equation right here, this is all ready to go integration wise. The only catch here is that the CV term is temperature dependent. And if you want to go any further with an analytical result, you've got to assume that it's not. And so that's where we started with solving this thing. So the gamma term is often introduced at this point. It's a ratio of the constant pressure to constant volume, ideal gas heat capacities, and there's all sorts of substitutions that we do there. So once you substitute gamma into the last equation I highlighted, we get to this point. And then once we integrate it, the dt over t turns into a logarithm, and so does the dv over v. And so this is the final integrated form, and then we're ready to do calculations with that. And so just algebraic manipulations of this equation get you to all of the equations in chapter 3 that look kind of like this, where the product of 2 of the state variables to some exponent is equal to a constant. All right, so if I want to solve for T2 given my initial and final volumes and my initial temperature, I've just got to solve this thing for temperature. And so that's where we can start today. So in my rush to get a number in front of you on Wednesday, I got the numbers right, but I made a little goof with the calculation. So I wrote gamma minus 1 up there, and that's backwards. And let's see why that is. Let's see if I can copy this and bring it down. Come on, you. Copy. Come back. Yes. All right, whatever. Let's try it again. So we had 1 over 1 minus gamma, and then we had the natural log of the temperature ratio equals the natural log of the volume ratio. All right, so the factor over here, I multiply both sides by that factor, and then I want to tuck it into the logarithm. So natural log T2 over T1 equals natural log all right, you see that? So that's just multiplying both sides by 1 minus gamma, and then using logarithm manipulation rules to bring the 1 minus gamma factor up into the exponent. Now I can exponentiate both sides. And so I'm going to get T2 over T1, oops, equals V2 over V1, 1 minus gamma. And when you look in the equations in the book, they don't write it like this. They write it like this. T2 over T1 equals V1 over V2. And gamma minus 1 then is the negative exponent there. And that's why they write it that way. So at any rate, your T2 is going to be T1 V2 over V1, 1 minus gamma, or if you like it the other way, you can do it the other way. And so that's going to be 298 Kelvin. And my compression factor was 4, so the ratio of V2 to V1 is 0.61 over 2.44, or 0.25. And one minus gamma. The gamma that I'm using is 1.31. So that was the gamma that we calculated at 298 K. So that's 298 Kelvin times 1 over 4 to the negative 0.31 power. So if you use the SVA version, then it's the same thing. It's just 298K times 4 to the 0.31 power. And that's where we get to our 458 Kelvin. Okay, so we got to that result, remember, by assuming that the heat capacity doesn't change with temperature, and therefore the value of gamma does not change with temperature. We've got a correlation for heat capacity with temperature that tells us that, well, it is important and it does change. And the last thing that we calculated before leaving on Wednesday was what the value of gamma becomes at our estimated final temperature of 458 Kelvin. And it's about 1/10 of a point lower than it was at the initial temperature. So if we go and calculate what the T2 would be, so this is a question, what if we used gamma 458 instead of gamma 298. So that would be T1 or T2 equals T1 times V2 over V1 times 1 minus gamma 458, which is 298 times 4 to the 1.227 minus 1. And that comes out to be 427 Kelvin. So that's about a 30 C difference. All right, so you see the problem here. So the neglection of that temperature dependence gives me a bound of 30 degrees of uncertainty. You know what my final temperature is, and that is significant. That's 30 C is the difference between hot water and freezing water, right? Okay, so any proposals as to what to do to get a better estimate? So using the cold heat capacity is probably going to give me one limiting case, and using the hot end heat capacity is going to give me another limiting case. If I want to use a constant heat capacity or a constant gamma and get a better estimate for temperature, any proposals for what I could do? Yeah. I can average out the gammas, and that's perfectly reasonable. All right, so my average gamma would be 1.31 plus 1.227 over 2. Just for convenience sake, let's call it 1.23, and so that's going to give me 1.27 is my average gamma. So that's going to, at some point, this is going to be a gamma for some intermediate temperature. I mean, if everything was perfectly linear, we could just average the initial and final temperatures and then calculate the heat capacity at that average temperature, and it would be perfect. That's going to be close-ish, but it's not going to be perfect. So we're going to get to a better answer here, and it's actually going to be a pretty good answer. But I just want to point out that it's not going to be mathematically, analytically exact. Yeah, Anna? That should be in the exponent, sorry. Okay, so using an intermediate, gamma is going to give us T2 equals T1 times V2 over V1, 1 minus our average gamma, which will be 298K, times 4 to the 0.27, and that is going to come out to be 433 Kelvin. Okay, I am going to assert right now that the exact answer is within 1 degree C of 433 Kelvin. I think I might have enough time to play with to actually show you how to get to that exact answer. All right, so to get to that exact answer, well, let's go back to this point up here before I made any assumptions. Let me do this. No pasting allowed today. I don't know what's going on. All right, so if I don't want to have any assumptions about the temperature constantness of the heat capacity, I can just integrate both sides and see how far I get. So if I integrate the right side and put on the left, I'm going to have a log V2 over V1 like I did before. And on the right side, I've got an integral. It's going to go from T1 to T2, 1 over gamma minus 1 dt over t, or in final form, it'll be V2 equals V1 times e to the minus T1 to T2, 1 over gamma, and I'll explicitly put the temperature dependence in there to remind us that there's no pulling that constant out of the integral anymore because it's no longer a constant. And so at this point, it looks like I might be stuck because I don't know T2, but let's think about this. This is known. This is known. The gamma function is known. T1 is known. The only thing that's not known is T2. So I have one equation and one unknown. So this is just a nonlinear equation to solve. So the integral part of this can be evaluated numerically. So the procedure is going to look something like this. We're going to guess T2. We're going to evaluate the integral. We're going to evaluate the right-hand side of the equation. So if T2 is correct, then the right-hand side is going to be equal to the left-hand side, which is just V2, right? So if not, we're going to have to re-guess T2. And that sounds like an awful lot of work, but that's exactly what numerical solver routines do, both in calculators, both in spreadsheets, so like in Excel, and lots of tools in MATLAB. So I will demonstrate how you do that. We'll use MATLAB. I want to show you something in Excel, but I just, it'll probably take 10 minutes to get through. And I can do this in MATLAB really quickly. Okay, so All right, can you see the bottom of the screen there? And is the text big enough, or should I make it bigger? All right, let's see if I can get it a little higher. Stay. All right, better? Okay, so these were the heat capacity constants for methane again. And to calculate gamma, I need an equation that I can use to calculate the heat capacity. So Cp over R, remember I showed you this once before. We're going to construct a function handle. So that's a function that will evaluate a number and pop out another number. So the expression is going to be the heat capacity equation. So CPR is the ideal gas heat capacity divided by the ideal gas constant. And that's the A plus the B times the temperature plus the C times the temperature squared. And so gamma, that's Cp over R divided by Cv over R. For an ideal gas, Cv is just Cp minus 1. Cv over R is Cp over R minus 1. So gamma is going to be another function handle. So I'm going to give gamma a temperature, and it's going to spit out a gamma. So that's going to be Cp over R evaluated at temperature T, and then that's going to be divided by Cp over R evaluated at temperature T minus 1. So just to show you that that works, if I say gamma of 298, I get 1.31. That's what I had calculated earlier. Gamma at 458, that's 1.227. That's the number I had in the notes earlier. And gamma at 433, that was, and we haven't calculated that one, but for example, that turns out to be about 1.24. Okay, so just to get what I've done so far back up where you can see it. All right, so now that I got gamma, the next thing I want to do is I want to make something that can take a guess temperature for T2, evaluate the numerical integral for me. So that's going to be yet another function handle. So my integral, we're going to be taking a guess for T2, and that's simply going to use the MATLAB numerical integrator, function called integral. And so we're integrating with respect to t. And so the function we're integrating is 1 over, I'll make sure I got the, 1 over 1 minus gamma evaluated at temperature T times 1 over temperature. All right, this expression right here, if we go back to the notes, is just the integrand, right? So I took the minus sign, and it's 1 minus gamma instead of negative gamma minus 1. The variable that the integral function is integrating is t, and that's why I have let me out. There we go. That's why I've got t right there, so it's distinct from the upper limit. And then the arguments to integral are going to be the lower bound and the upper bound. And the upper bound is provided by the argument to the function. So when I enter that in, my integral is now function handle. So if I say my integral, and I want to see what it turns out to be at an upper limit of 433 Kelvin. I told you that was going to be pretty close to the right answer. I got to spell integral right? What did I do? I sure did. One more time. There we go. All right, so now to see if that's right or not, I've got to take V1, which is 2.44 times the exponential of my integral evaluated at 433, and it comes out to be really close to V2, right? So that's V1, and then that's the right-hand side of my equation. So I just evaluated that right-hand side, just like step 3 says. All right, now the bullets say if it's correct, then I'm good. If it's not, then I have to re-guess T2. All right, so what if I'm not satisfied with that level of accuracy, or if I hadn't done some homework up front to figure out that 433 was going to be a really good guess? I would like not to spend all day guessing numbers coming out with the right value. So what I'd rather do is I'd rather have MATLAB do the guessing for me, or if I'm doing something similar in Excel, I want GoalSeek to do the guessing for me. Or if I'm feeling more sophisticated in Excel, I can activate the solver tool that it comes with that's hidden by default. So what I'm going to do instead now is, and you'll get to this in 310, the basic idea for solving nonlinear equations is to subtract the left-hand side from the right-hand side and so that becomes a function, and the root of that function is where the function evaluates to 0. So the difference between V2 and V1 times this exponential is 0. That means this equation is satisfied and I've chosen the right value for temperature. So if I say 0.61 minus that expression, this new expression here is a function that I'm evaluating at 433, and it comes out to be a number that's close to 0, but I might argue that it's not quite 0 yet, and I would like a better approximation of 0. So I'm going to use MATLAB's function for finding roots of expressions. It's called F0, and I'm going to tell MATLAB, and it requires a function handle yet again. So I'm going to feed it the expression I want to zero out for me, and I'm going to tell it what variable I want it to use to do that zeroing out. So I want to find the value of T2 such that 0.61 minus 2.44 times the exponential of my integral evaluated at the undetermined T2 is equal to 0. And then to get things started, I have to give it an initial guess. So say I have no clue, I'll put in maybe 300 Kelvin. I have no idea what the final temperature of this adiabatic compression is going to be. And it goes, and it comes out with the right answer. All right, so the right exact answer here is about 433.5 Kelvin, which is well within the 1 degree C that I promised there. Okay, so it's really not that bad to include the temperature dependence of the heat capacity if you're using numerical tools. All right, any questions about that? All right, and what I'll do here is I'm going to I'll just copy and paste this code into an M file, and I'll plop it into the lecture notes folder, and you can look at it later. Okay, so that pretty much wraps up the background work that we need to do to talk about state changes. And the last thing that we'll talk about before we go on to the next great topic, which is, how do you actually use these state changes to calculate some useful properties? And that's when we'll get into the second law, and we'll start talking about refrigeration and heat engines and turbines and compressors and all that great stuff. If we want our property calculations to be accurate, we've got to go beyond ideal gas law. And so we just want a real quick refresher as to what are some of the various strategies we can use to go beyond ideal gas law. So first of all, this is a question that you should all have a good answer for by now. So, when is the use of the ideal gas law appropriate? Yep, that's a qualitative answer. So high T and low P. There's a rule of thumb that we teach in 210 to actually check a number that tells you if you're good or not. It's a rule of thumb that says if you satisfy this criterion, then you should be within 1% error as far as calculating the molar volume goes. Yes. Yep. So V IG is RT over P. So if you're given a T and a P, you can calculate what the molar volume for the ideal gas would be. So if this comes out to be greater than 5 moles per liter for simple diatomic gases, then the rule of, and this is not a law, this is not a rule. Yeah. That's correct. And for other gases, the rule of thumb says 20 liters per mole. Okay, so that's not anything that has a mathematical proof or anything. That's just observation. Okay, so that's a good thing to check. Ideal gas is also appropriate when you're doing state path calculations. So it's not all just something easy that you learn and then you never use because it's not actually useful. It's always useful, even if you're dealing with real gases. So we will use ideal gas as a state. And we're going to do that over and over again. So the general idea is we're going to have an initial state, and we're going to have a final state. And both the initial and final states might be real gases, or one side might be a liquid and one side might be a gas, but let's just say they're both real gases for now. And we want to calculate work, heat, entropy change, enthalpy change, all that good stuff as we go from state 1 to state 2. The easiest way to do that is to imagine some intermediate states that have the same temperatures and pressures as the real states, but instead of real gases, they're ideal gases. And so this isn't a real state change, this is an imaginary state change. But suppose you had a magic wand that could remove all the interactions between molecules, so they just acted like completely independent particles, and that's what the ideal gas approximation is. Then you can use all the wonderfully simplified math for manipulating ideal gases, and then you only have to worry about this transformation from real to ideal, and then ideal back to real. All right, and we're not going to talk about how do we wave that magic wand just yet. I will tell you that in order to wave that magic wand, we will need accurate equations of state that give us the correct relationships between VT and P. Once we have that equation of state, they will help us calculate the property changes that we need to calculate to wave that magic wand. Okay, so the ideal gas law is the easiest one. And if we look in chapter 3, a lot of what chapter 3 talks about is various other equations of state. So if we go into chapter 3, we talk a little bit about virial equations of state. And the general idea there is if you look at the PV product, rather than just saying it equals RT, you do a power series expansion, just like you do in calculus. And we don't know what all the coefficients are, ab initio anyways. We know that the constant term is probably going to be RT, right? And you can expand this in terms of pressure, in terms of volume. They're both independent variables. And then if you can come up with a clever way of determining what some of the higher order terms are, the more of these coefficients that you determine, the more accurate you're going to get to what a real gas is. We don't use those an awful lot, so we won't spend a lot of time talking about the virial equations, although remember that they exist because they become useful for certain derivations. Okay, the first cubic equation of state that we see is the van der Waals equation. And so all this one does is it takes the ideal gas law, and first of all, it looks at the denominator term. And it says, the first way to account for the fact that a gas is a cloud of particles that have no idea what else exists in the universe is to first of all account for the fact that each particle occupies some volume. And you can't infinitely compress particles together because at some point they're going to start to crowd. And so that's what that B term is. So without the B term there, as you crank the pressure, you can do that indefinitely, and what the ideal gas law says is the molar volume is just going to go to 0. And what the B term does is it makes the equation explode before that happens. So as the molar volume approaches this value of B, the pressure becomes infinite. And that's a reflection of the physical observation that you can't just keep compressing gases indefinitely. And then the second term is the first attempt at accounting for intermolecular interactions. So 1 over V, that's got units of moles per liter, or if you go down to the particle, that's going to be particles per volume, right? So that's a number density. 1 over V is a number density. So if I were to put my finger at any random point in space, 1 over V is the probability that I'll find a particle there. So 1 over V squared then is the probability that I found a particle where I'm pointing and I found another particle right next to it or right on top of it. So 1 over v squared is going to be proportional to the probability of finding two particles that are close enough to each other to interact with each other. So that's all that is. So 1 over v squared is just the probability of finding two particles next to each other. And then all A is how much reduction in pressure is there as a consequence of those particles sticking to each other. So that's how you can think about that. And at this point, both the ideal gas law and the van der Waals equation really, other than the A and the B constants, are very similar. And moreover, they both predict that all gases are going to behave exactly the same way. Their chemical identity doesn't matter at all, except for how you calculate A and B. And if you look at how A and B are calculated, that goes a little bit later in the chapter. I want a number of different pages here. I'm back in Virial now. Where'd you go, van der Waals? I think I've got to skip up to the full table. Yeah, here we go. All right, so that A parameter, you see that the only two constants in there that depend on the identity of the fluid are the critical temperature and the critical pressure. And likewise, the B parameter only depends on the critical temperature and the critical pressure. So there's the only two parameters that actually have physical measurements embedded in them. And the fact that it works pretty well for a large number of fluids is recognized by what's called the corresponding state principle. And that's elaborated at more length if you read chapter 3. And it doesn't work perfectly, though. And so there's this omega factor that Pitzer and coworkers introduced a number of decades ago. It's called the acentric factor, and it's also called the Pitzer acentric factor. It's an additional property, and the text explains how it's defined and how it's measured. But it's basically one extra parameter that accounts for molecular uniqueness of various gases. And so depending on which equation of state you use, you get to include an omega or not, and you're generally going to expect that the equations that include the omega term are going to be more accurate because they're accounting for more of the specific details of the actual gas that you're using. Okay, so the full form of the cubic equation of state you've seen before, and so again, I'm not going to elaborate on it quite a bit, but this is the general form of the cubic equation of state. So they look an awful lot like van der Waals equation. The main differences being that you've got some extra decoration in the 1 over v squared term. So they're corrected by another multiple of b. So these sigma, the sigma and the epsilon terms are equation of state dependent. And the interaction parameter, the A term, that's also very equation of state dependent. So the acentric factor is going to appear in that A term if it's being used. All right, so if you've got a temperature and a volume, it's easy to use this to calculate pressure. It's more challenging to calculate the volume if you're given a temperature and a pressure, which is usually the case. A really convenient way for solving is presented on page 99. So this is in section 3.6. So equation 348 and 349, they take the general form of the cubic equation of state, and they introduce the beta parameter and the Q parameter. So those are just algebraic simplifications to keep the math a little cleaner. So they're dimensionless versions of A and B. So beta is the dimensionless version of B, and Q is the dimensionless version of A. And with some algebra, you can arrange it in one of two ways. And depending on which way you arrange it, you actually get yourself a built-in numerical method for solving for either the liquid or the vapor root. So if you look at, so if you read the text up here, so equation 348 says that if you start with the initial guess of z equals 1, so you've used z before, right? So that's a compressibility factor. So it's just the ratio of PV to RT. So it's 1 for an ideal gas. So if you start with a value of z equals 1, substitute it on the right-hand side, you're going to calculate what that value is, and it's going to come out to a number. It might come out to the value of 1. If it comes out to the value of 1, then that means that the right-hand side and the left-hand side evaluated the same number and the equation is satisfied. It's probably not going to come out to 1. Maybe it comes out to 0.9. So what you're going to do is you're going to take that result and you're going to plug it back in there for a second round of calculation. So you're going to reevaluate this right-hand side using your value of 0.9, and you're going to get a new value out. So maybe it's 0.905. So it hasn't changed very much. So you're going to take that new value and you're going to plug it in again. And every time you repeat that, the value that comes out is going to get closer and closer to the value that you put in. And so it converges on a single value of z. And what the book asserts is that the final value of z that you get is going to be able to give you the correct molar volume of the gas phase. Now, a little bit later on, we're also going to want to be using cubic equations of state to evaluate the properties of liquid phases, and that's one of the neat things about the cubic EOS is it's not just for gases. You can model liquids with it pretty well too, and that's incredibly useful to be able to model both liquids and gases, especially when you start to talk about modeling separations processes where you've got mass transfer between liquid phase and gas phase happening all the time. So some other rearrangements to 348 gets you down to 349, and it's the same equation, it's just rearranged differently. So this time what you're promised is that if you start with an initial value of z equal to beta, and then you apply that same iteration process, what the value of z that's going to be converged upon is not going to be the vapor root, it's going to be the liquid root. So you actually will be able to calculate what the molar density of the liquid is by using the 349 version. All right, so I think that's good for this week. So on Monday, we might do a quick example illustrating this calculation, but it's pretty straightforward. And then we're going to march right forward into talking about heat engines, and that's it's a great way to introduce the concept of the second law, and we'll start talking about entropy then at that time as well.